Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, we will continue for the lecture of topic uh, Bernoulli equation, which is the next is general energy equation. As we know of first law of thermodynamics, it shows it, uh, the first law of thermodynamics is known as the conservation of energy principles, and it states that energy cannot be created nor destroyed, but it can be changed in the form. Okay, this is an example of how the energy being transformed. Okay, if you can see here, we have energy in minus energy out should be equal to the differentiation of energy. For example, we have this example of there is a rock, say it's a free fall. Okay, from beginning, the potential energy is about 10 kilojoules, and kinetic energy equal to zero because there is no movement happen. The moment the the moment the rock is falling down as free fall, there is a change of energy from the potential energy reduced to 7 kilojoules, and the rest is changed towards kinetic energy. So this is proven that total up of the energy should be the same, which is 7 plus 2, which is 10 kilojoule. So it shows potential energy being converted in kinetic energy. Okay. So this is a general equation of energy, which is you will have a Q. Q is the net. The net. Q is the net in. Q net in. Q dot net in is Q dot in minus Q dot out, which is the net rate of heat transfer change. Okay, while second one is W dot in, net in is equal to W dot in minus W dot out, which is net power of input to the system. Okay, so it should be equal to the changes of energy. Okay, the rate of change in energy. Okay, so we can also say that Q dot in net in plus W dot net in equal to differentiation in terms of time, integration in terms of time of rho energy dV. So, for example, in this figure, we can see that in this figure, based on this equation, we know that Q dot in plus Q dot net in plus W dot net in is equal to delta E. So in this case, our Q dot in not net in, should be equal to Q in minus Q out. So from here, Q dot in minus Q dot out. From here, we can say that the Q dot in is 15 kilojoule. Okay. Minus Q dot out is 3 kilojoule. So the total will be 12 kilojoule. Meanwhile, for the W dot net in, we know that it's the same, it's the equation of W dot in minus W dot out. So in this case, W dot in is 6 kilojoule, but W dot out is 0. So total is 6 kilojoule. So based the main equation, we know that the delta E is equal to W dot net in, which is 12 kilojoule, will be minus by W dot net in work, which is 6 kilo. Sorry, will be plus, okay, plus 6 kilojoule. So the total will be 18 for the general energy equation, next is about energy transfer by heat. So we know that the moment energy transfer happen, it should be related with heat transfer. For example, this is soda tin. We have a soda tin of temperature 5 degrees Celsius. So when we put it outside in the room temperature, in order this soda tin to be equally has equal temperature with the room temperature, heat is transferred into this soda tin. For example, for 5 degrees of Celsius, we need 16 joule of per second heat in order to change the temperature of the soda tin into 25 degrees Celsius, which is room air. For example, if the temperature is 15 degrees Celsius, so the energy needed to increase or to ensure the temperature will be similar like room temperature is about 8 joule per second. Means that the lower of the temperature of the soda tin, the higher energy needed to be supplied in order to have a similar temperature with room temperature. For example, at the end, the soda tin have a similar room temperature. At this moment, there is no heat transfer happen. Okay. Okay. This is the equation of energy transfer by work. Okay. Just now is energy transfer by heat. We learn. So this one is energy transfer by work. Okay. Energy transfer by work. The equation is W total, work total is equal to work shaft plus work pressure plus work viscose and also plus other works. Okay. Work shaft is the work transmitted by rotating shaft. For example, you have a rotating shaft, so there will be a work done by shaft. So you need to include the work shaft. So work pressure is the work done by a pressure force of control volume. And the work viscose is the work done by the normal and shear component of viscose force of the control volume. And other works such as electrical work, magnetic work, surface work, and rest. So all this work should be add up in order to get the total of work. For example, this is example of piston. Okay, so for example, there is a shaft happen. Shaft, the work of shaft to ensure the piston head to be movement should be included, plus the work pressure. The work of pressure, okay, pressure in order to force this piston head to be going down. Works of viscose normally is, for example, there is a shear or friction happen at the movement, okay, and work of others depends on, for example, additional works. So the total will get based on the addition of all works. Okay. Okay. For a typical engineering problems, the control volume, this is for example, control volumes should have an inlet and outlets. So we should have an inlet of mass flow rate energy inlet, and we have an outlet. Okay, energy flow in each inlet and energy flow of outlets entering the control volume through the heat transfer and net work shift means that for the fixed control volume, okay, we will have a Q dot net in, okay, based on heat, and also W dot net in. We also have energy from mass flow rate. For example, the flow going inside is energy M in, M dot in, and also M dot out. So all these things should be included. What in should be goes out in order to get the equilibrium results. Okay. So this is the term of energy transfer. For example, isothermal. Isothermal is the temperature of system remains constant during the energy change of time of a system. Means that if the system have a similar or constant temperature during energy change, we call it isothermal. For isentropic is the fluid flow that is both adiabatic and reversible. Means it can have a no change of heat and also reversible. And adiabatic means that no transfer of heat between the system and its surroundings. Means the Q equal to 0. There is no heat transfer happen. Okay. For the energy for steady flow, okay, this is focused on steady flow. The equation, the time rate of change of energy content of the control volume is 0. So for steady flow, the delta E should be 0. So means the Q dot in net plus W dot shaft net is equal to summation of output minus summation of input. Okay, this is the formula. So this is, for example, you have a fix of control volume. The Q dot in, okay, means the energy from heat and energy from work going inside, okay, should be the same as summation of out, all the energy out, okay, during a mass, due to the mass, minus all the energy in. Okay, so if the energy flow with mass out is similar like the energy flow of mass in, means that there is be equal to 0, means that there is won't be energy left inside of the control volume. But okay. Okay, this is an example of mechanical energy flow chart for fluid system that involve pump and turbine. So if you can see here, okay, we can divide it into two. For example, okay, for the left side is all the energy going in. For example, we will have a water pump energy. We also have a energy of mechanical fluid. Okay, and for the right side is the output. Okay, if you can see based on this formula, we can see that the mechanical in, okay, plus the work by pump is equal to turbine energy, okay, plus mechanical fluid out and also losses. So if you can see here, mechanical in, okay, plus what is in should be going out, plus the pump in is equal to, on the right side, okay, this is left side, this is, okay, on the right side is the equally the output. First is the mechanical output, then the turbine energy work, and also losses of all the losses. Okay, all the losses. Okay, so this is the formula of mechanical energy flow chart of pump and also turbine. Besides of that, this equation also can be simplified in terms of heat pump or heat losses. So based on here, we know that H pump U is equal to W pump U divided by G, or W dot pump, okay, divided by M dot G, mass flow rate dot G. So if this equation, okay, in order is replaced here, for example, the equation 5.76, okay, all this equation we will divide it into m dot g. Okay, so what we'll get is this equation. Okay, so in order to 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 change the equation or simplify the equation in terms of head delivery. Okay, for example, where head pump. Head pump is the useful of head delivery of system pump because of the irreversible losses in pump. Okay, then head turbine. So this one all divided by m dot g, you will get another simplified equation in terms of head. Okay. Okay, we go for the next example. Okay, the first example is about there is a pump. Okay, okay, the pump of water distribution have a 15 kilowatt of power, okay, with efficiency of 90%. So the flow rate through the pump is about 5 liters per second, and the diameter is there is no change of diameter inlet and outlet, and also if the pressure of the inlet and the outlet of pressure with 100 kilopascal for the inlet and 300 kilopascal for the outlet. Question number one is calculate the mechanical efficiency. Number two is the temperature rises of water as it flows through the pump due to the mechanical efficiency. Okay. When we get these questions, so what we need to do is we need to understand for question A, okay, we need to find mechanical efficiency. Okay, mechanical efficiency, we need to know the equation. Okay, the equation of mechanical efficiency. Okay, mechanical efficiency of pump is equal to delta energy, okay, the change of energy of mechanical fluid divided by work of pump, okay, of shaft. Okay, so we need to find both in order to get the mechanical efficiency of pump. Okay, that's the first step. So the second step, we need to try to find one by one. First, we try to find the work, okay, mechanical of shaft, okay, which is pump shaft. So the equations give us that this equation is equal to mechanical of motor, efficiency of motor, times work by electric. So in this case, the efficiency is 90%, 0.9, should be times with the electrical power is 50 kilowatt. So the total should be only 15.5 kilowatt. Okay, so we have here what W dot pump. Okay, the third one is we need to find delta E mechanical. Okay, here we can use the equation of delta E mechanical. Okay, this equation. Okay, from here we know that delta E mechanical field is equal to E dot mechanical out minus E dot mechanical in. So in terms of equation, we know that m dot P2 divided by rho plus alpha 2. Alpha is a factor of energy. Okay, V2 divided by 2 plus GZ2 minus m dot P1 divided by rho plus alpha 1 V1 squared divided by 2 plus GZ1. Okay, based on here, we know that there is no change of uh, velocity. Okay, the velocity is the same. So there is no change of velocity. Means okay, we can cancel it because there is no change. So in and out it should be the same. Okay, this one is cancelled. So same as kinetic energy. So cancel. For potential energy also cancel. So at the end, what we'll get is what will remains is m dot E2 E2 minus P1 divided by rho. Okay, so this is the equation that we need to solve. So we already know that P2 is equal to 300 kilopascal, P1 is equal to 100 kilopascal. So we need to find m dot. So m dot is equal to rho dot v dot, means that volume flow rate. So we assume that the rho is 1 kg per liter, should be times the volume is on here. He said the water flow rate, the volume flow rate liter per second is 5 liter per second. So it should be 50 liter per second. 50 liter per second. So at the end, we will get around 50 kg. So here we can find our changes of mechanical energy, which is m dot is 50 kg per second times is 300 kilopascal minus 100 kPa divided by rho. What is the rho is 1000 kg per liter. Okay. 300. So here is m dot. So in order to find number 4 is calculate here efficiency of pump, which is energy of mechanical fluid. Oh sorry, this one should be the answer should be is about 10 kilowatt. So energy of fluid is 10 kilowatt divided by work done by shaft is 13.5 kilowatt. So at the end, you'll get the mechanical efficiency is about 0.741 or 74.1. Okay. Okay. For question B is what is the temperature effect based on the mechanical efficiency? So here, based on our calculation, okay, the mechanical power supply is W dot pump shaft dot pump shaft is equal to 13.5 kilowatt. Meanwhile, the delta E mechanical fluid is 10 kilowatt. So we know that the losses happen is energy mechanical losses is equal to W dot pump shaft minus delta E mechanical fluid. So 13.5 kilowatt minus 10 kilowatt. So we will get 3.5. So this is the losses happen due to the mechanical efficiency, friction or something. So in order to calculate the temperature, okay, the formula of mechanical losses is equal to m dot U2 minus U1 or m dot C delta T. Okay, so delta T is equal to mechanical losses divided by m dot C. So mechanical losses is 3.5 kilowatt divided by flow rate is 50 kg per second and C is 4.18 kilojoule per kilogram per delta C. So total you will get 0.017 delta C. Okay, we go for example 6. Okay, example 6 is a equation of a fan, okay, which is selected to cool a computer case whose dimension is 12 cm times 40 cm times 40 cm. Half of the volume in the case is expected to be filled in the component, which is the diameter of 5-meter diameter hole is available at the back of the case for installation of the fan that is replaced to replace the air in the void spaces of the case once every second. Small, low power fan motor combined units are available in the market and their efficiency is estimated to be 50%. Okay, the question is find the weightage of the fan motor unit to be purchased. Okay. Okay. Based on the question, we need to find the motor of electrical power. So W in, what is the motor in, is equal to, first you need to put the final equation to be used, divided by W in divided by W out. Okay, W in okay, W in is equal to W out divided by efficiency of motor. So we know that the efficiency of motor is equal to 30% or 0.3. So in order, we need to find W dot out. In order to find W dot out, we need to use the energy equation, which is m dot E1 divided by rho plus alpha 1 V1 squared divided by 2 plus EZ1 plus W dot in is equal to n dot E2 divided by rho plus alpha 2 V2 squared divided by 2 plus VZ2 plus energy mechanical loss. Right. Okay, from here, based on the equation, we know that there is no change of pressure, there is no change of elevation of potential energy. So here is our P1 and P2 should be the same. So means P1 we can cancel, and P2, GZ1 also can be cancelled, GZ2. And another one, the velocity one is assumed to be 0, and velocity 2 we have because of the jet flow effects. So at the end, what will the next equation that we simplify equation is W in dot E is equal to m dot alpha 2 V2 square divided by 2 plus E mechanical losses of time. Okay, we have another equation that we know that W dot in minus losses, mechanical losses of fan is equal to W dot out. So if we replace this equation inside of this, what we'll get is W dot out minus E dot mechanical loss of fan is equal to this equation, is m dot alpha 2 V2 squared divided by 2 plus E mechanical loss fan. So mechanical loss fan, so this one is should be a plus here, okay, because here this one is going to right side, we get plus here. Okay, so mechanical loss fan can be cancelled at the end. What we'll get, our equation of W dot out is equal to m dot alpha 2 V2 squared divided by 2. Okay, so this is the equation that we will use. So in order to solve this one, you need to find your m dot, you need to find your V. Okay, so how to calculate m dot? M dot is mass flow rate. Here we know that m dot is equal to rho volume flow rate. So we need to calculate volume flow rate first. Okay, so volume flow rate is equal to volume divided by delta T. So the volume is 550%. Okay, from from here we know that volume, we know that volume is equal to, the question said that only 50% of the air, 0.5, 50%, or 1 over 2, it should times with the volume, 40 cm and 40 cm. So here you will get the volume in terms of meter cube per second, or is 9600 centimeter cube per second. If you change, it become 9.6 times the power of 10 negative 3 cube per second. And it says that for volume, it said that the volume in through the rate of in 1 second. So volume flow rate is 9.6 times power of negative 3 meter cube per second divided by T is 1 second. At the end, you will get your volume flow rate is 9.6 meter, 9.6 So 9.6 times power of 10 negative 3 meter per cube second. So in order to get your m dot, so the answer is your rho is 1.2 kg per meter cube times this 9.6 times power of negative 3 meter cube per second. So your mass flow rate is 0.0115 kg second. So okay, next we need to find okay next we need to find the velocity. Okay, next is the velocity. Okay, we know that velocity volume flow rate is equal to v equal to velocity times a. So in order to get the velocity is v dot divided by a. So you need to find your a. Okay, your a is this one, which is your pi times d square. D square is 0.05 meters cube. So you get your area is 1.96. So automatically, when you're based on your volume, you divided this area, so you will get your velocity is 4.9 meters per second. So back to the equation that we need to solve. So the answer for W dot out is m dot is 9.6 times power of negative 3 times alpha 1. Alpha is assumed to be 1. Okay, sorry. This small mistake. Okay. Based on this equation, the m dot is this one, 0.0115 times the alpha 2. Alpha 2 is 1.1, then the velocity is 4.9 meter per second, power of 2 divided by 2. Okay, so at the end you will get the W out is 0.152. So in order to find your W dot in, you put everything in the same equation, which is W dot out. W dot out is 0.152 watt divided by 30% efficient is 0.3. At the end, you will get your electrical power is 0.506